So with energy of combustion being the focus of chapter 6, back in chapter 2, we studied about chemical reactions, and we learned the different types of chemical reactions, and combustion reactions was one of those. And we learned that when a substance combusts, there must be a reaction between that substance and oxygen. And then we also learned that if the substance being combusted is hydrogen gas, H2, that your product is going to be water vapor. And we saw that demonstrated in one of our labs early in the semester on a video with the hydrogen gas being produced by a reaction and then being used to fill a balloon and then igniting the hydrogen gas and seeing the explosion. And so depending on the substance being combusted, you're going to get certain products. And so we touched on it back in chapter 2, and we'll really go in depth in studying hydrocarbons in chapter 6. Hydrocarbons are a specific type of substance that undergoes a combustion reaction, and hydrocarbons are fuels. And so when fuels like hydrocarbons are combusted, they produce carbon dioxide and water. So we're going to be focused on fuels, and we're going to define what fuels are, and our focus is going to be studying how much heat or how much energy is released when specific types of fuels are burned. And then we're going to have another part of the chapter that we'll look at that focuses on how electricity is generated by combusting certain types of fuels. And then we'll also touch on some environmental implications of obtaining and using fossil fuels for energy, and also the benefits and overall sustainability of using alternative sources for energy other than fossil fuels, like biofuels. So we'll talk about what biofuels are and what are the benefits of using biofuels versus fossil fuels, and are biofuels a significant and logical alternative to fossil fuels. And so for the third chapter exam, which will cover chapters 6 and 7, I have provided a bonus opportunity. And basically you'll want to watch this video. And then the bonus consists of 3 questions that are shown here. And I've set the bonus up as an assessment in eLearn. And so in eLearn, you'll just click down the down arrow on the activities tab and then click assessments. And then you'll see the third chapter exam bonus. And I think I gave you until December 4th to do it. So you can wait until after we're done with chapter 6 before you complete the bonus activity. And December 4th will be, of course, that's the last day of the semester. So you have until the last day of the semester to complete that. So fuels are basically any substance. It can be in solid form, it can be in liquid form or gas form. And if you can combust it and obtain energy from it, you can consider it a fuel. So basically, the substance has to be able to undergo a combustion reaction. Fossil fuels are a special type of fuel that were formed millions of years ago from decaying plant matter. And so before the plants decayed, they underwent continuous photosynthesis reactions. And by using that energy from the sun, as well as carbon dioxide and water vapor in the air, plants are able to synthesize their own food that we call glucose. And so plant material that has undergone partial decomposition after being subjected to heat and pressure, that is how coal and petroleum were produced from these decaying plant matter. And so petroleum consists of a variety of substances that can be separated via a process called fractional distillation. So we get our kerosene, our jet fuel, our gasoline, our propane, and so on and so forth. All of these different products from petroleum, which we also call crude oil. Now, when herbivores digest plants, the glucose in the plants react with the oxygen that organisms breathe in, and then the products are carbon dioxide and water, and also energy. And note that metabolism, its reaction is basically the opposite of photosynthesis. It's just photosynthesis in reverse. So photosynthesis requires the absorption or use of energy. Whereas metabolism results in the release of energy. And so this metabolism reaction is identical to decay and combustion reactions involving glucose. So taking a look at a few questions, list 5 fuels. So when I say the word fuel, what's the first thing that comes to your mind? Anyone can answer.
Gasoline.
Okay, gasoline. Gasoline is a mixture of some different components of crude oil, but it's mostly octane. And so when you go and buy your gasoline, there's a rating on the fuel pump, 87 or 89 or 91 or so on and so forth. That tells you what percentage the gasoline is octane. So if you buy 91 gasoline, your gasoline is 91% octane. The other 9% are other components of petroleum like heptane, hexane, so on and so forth. What's another fuel?
Kerosene.
Very good. Kerosene. Kerosene is also a component of crude oil. Lots of people have kerosene heaters or lamps and so on and so forth. Coal is another fuel. About 80% of the energy that we use as electricity in this country, we obtain the electricity by burning coal. And we're going to talk more in depth about that process later in the chapter. We all have flown on a plane, or most of us, I'm sure. Jet fuel. It's also a component of crude oil. But what about our fireplaces? Good old-fashioned wood. That's a fuel. So we've got a nice list of 5. Can anybody think of some other ones that are kind of outside of the box, maybe?
Natural gas.
Go ahead. Go ahead. What did you say?
Natural gas.
Yeah, absolutely. A lot of people heat their homes with gas versus electricity. So natural gas is a good one. Natural gas is a mixture, but it's mostly methane. And we're very familiar with methane. That's one of the Lewis structures that we've drawn over and over again, CH4, as that perfect tetrahedral geometry. So we've got a nice list here. And so which of these fuels that we listed are derived from fossil fuels? Well, all of them except for what? Which of these fuels are fossil fuels directly or derived from fossil fuels? Well, gasoline, jet fuel, natural gas, methane, and coal, they're all fossil fuels. So all of them, except for wood. And wood is the only one that's renewable that's on our list. And so we talked about photosynthesis, in which the energy from sunlight is used by plants to convert the potential energy that's in the CO2 and water vapor in the air into glucose and oxygen. So 3 fuels whose energy originate from sunlight.
Solar.
Very good. Would you consider wood a fuel that originates from in sunlight?
Yes, it requires it to grow.
Right. The plants, the trees, where wood comes from, require sunlight to grow. Very good. Can we think of any others? Basically all the fossil fuels, right? Because the fossil fuels were made from once living plants. So basically sunlight is major, right? Basically all of the fuels that we use as far as to a great extent has some type of origination with sunlight, even the fossil fuels. So in order for these fossil fuels or the wood to participate in combustion reactions, now we've all seen wood burn. So we know that in order for the wood to burn, there must be some source of heat. So you got to have a match or one of the little strikers or some source of heat to act as an ignition source. Then of course you've got to have the wood, and then you've got to have an oxidizer, which is usually oxygen. When we say oxygen, we mean molecular oxygen, O2. So that's what's needed to generate a fire or to create a combustion reaction. You have to have a fuel, you have to have oxygen, and then you've got to have some type of ignition source, some type of heat source. That as a result of the combustion, you get products, and of course you get energy released. And most of the time, the products are CO2 and water. Not all of the time, but most of the time. But you always get energy. So we've formed a nice list of different types of fuels. Most of the fuels on our list are hydrocarbons. Even the wood can be considered a hydrocarbon or a modified hydrocarbon because wood contains sugar, glucose, Wood contains cellulose, and cellulose is a polymer made up of glucose units. So wood contains sugar. And so sugar is not a hydrocarbon because it contains oxygen atoms as well. But sugars are fuels because sugars can combust. So the majority of the different fuels that we placed on our list are what we call hydrocarbons. The gasoline, the coal, the kerosene, the jet fuel, the natural gas, those are all hydrocarbons because they are made up of only carbon and hydrogen atoms. The octane that makes up gasoline has the formula of C8H18. Natural gas is mostly methane, CH4. So those are hydrocarbons. They're composed of only carbons and hydrogens in their formula. And most hydrocarbons only contain single bonds. And so per every carbon atom, that carbon atom can be connected to 4 different other atoms. So most of the hydrocarbons contain only single bonds, and the carbons have 4 different bonds that they make with either other carbon atoms and or hydrogen atoms. So therefore, each carbon will have a total of 8 shared electrons, but there are some hydrocarbons that have double or triple bonds. These are called alkenes and alkynes, respectively. Hydrocarbons that only contain single bonds are called alkanes. Now, we can represent hydrocarbons many different ways. The most popular way is called the structural formula, which is just the Lewis structure that you show all of the bonds between all the atoms in the hydrocarbon. These are structural formulas. For the alkane, butane. Butane is a fuel that's often found in cigarette lighters. Now, another way to represent a hydrocarbons formula is by using what's called a condensed structural formula. Then there's a third one called a line formula. And so the condensed structural formulas don't show all the bonds. So those would be considered condensed. This one here doesn't show any bonds. It just shows you the atoms. Whereas this one shows you the bonds between the carbons. And then here is a line formula. And here is another condensed structural formula. All of these represent butane. The structural formulas show you all of the bonds between all of the atoms, whereas the condensed structural formulas, like this one's only showing you the bonds between the carbons. This one's not showing any bonds at all. It's just showing you the atoms. And then you have the line formula that doesn't show any atoms at all. It just basically shows you the arrangement. And so each end of this line structure represents a carbon atom, as well as each vertex. And so this line formula is telling me that I have an alkane, because I see all single bonds. If it was an alkene, I would see a double bond that would look like this. Or if it was an alkyne, it will show a triple bond like that. But because this is showing all single bonds, I know it's an alkane. And I know it's the alkane that has only 4 carbons. 1, 2, 3, and 4. So that's how you look at a line formula and tell which alkane it is, because you can tell how many carbons there are by the line structure itself. And so this little table here gives us the names of the first 10 hydrocarbons based on the number of carbons 1 through 10. So starting at 5 carbons through 10 carbons, the names are based on Greek prefixes. So the Greek prefix PNT stands for 5. Hex is 6. Hept is going to be 7. Oct is 8. And so you have the Greek prefix, and because these are single bond hydrocarbons, these are alkanes. So you have the Greek prefix plus the ending ANE. So 5 through 10, those names are easy to remember if you remember your Greek prefixes that we introduced when we were learning how to name molecular compounds back in chapter 2, I believe it was. Now, the first 4 alkanes are not based on any Greek prefixes. And so a lot of students use a mnemonic, MEPB, to remember those first 4. And they use the mnemonic, mother eats peanut butter. I don't know who thought of this way back when, but it's kind of stuck in chemistry, just like the Roy G. Biv for remembering the colors of the visible light in the visible part of the electromagnetic spectrum. And there's an Ulrich. If you go on and take the 2nd semester of this class or general chemistry, you'll learn about the mnemonic Ulrich when it comes to oxidation and reduction reactions. But that's a mnemonic that's kind of stuck on how to remember the first 4 alkanes. MEPB, mother eats peanut butter, for methane, ethane, propane, and butane. So when hydrocarbons combust, of course, you have to have oxygen that the hydrocarbon reacts with, and the 2 products are always going to be carbon dioxide and water. And so this is the combustion reaction balanced. We learned how to balance reactions back in chapter 2. So butane reacting with oxygen, producing CO2 and water. And so most fuels are a mixture, and it's not just one substance, totally one substance. So for most fuels, you have this mixture of different hydrocarbons. And so therefore the reactions are never quite this simple and cut and dry, but usually you have what are called side reactions going on as well. So like coal, for instance, contain mainly carbon. And so when coal combusts, it's mostly the carbon combusting. But then you also have sulfur in coal that will also react and form your sulfur dioxides, which of course are air pollutants. And also at high temperatures, like in your automobile engine, it gets pretty hot. When you're combusting your octane, you have this reaction going on. And of course, we need to balance it. But you have also other reactions going on, such as the nitrogen from the atmosphere also reacting with oxygen to produce nitrogen dioxide, which is also an air pollutant that's in smog. So usually you not only have the main fuel source, the main component of the fuel combusting, but you can also have different other side reactions taking place as well. So again, when we write a combustion reaction, just like I did with octane here, we also have to balance the reaction. So writing the reaction is pretty easy. We take our fuel source, we react it with oxygen, and our products are going to be carbon dioxide and water. But then we also have to balance. We have methane and also propane. So I'm going to let you go in your group meeting rooms and work together to balance these. And then question 2, we have a data table here to complete. What we're given are some condensed structural formulas that don't show any of the bonds. And so what we need to do is write the actual chemical formula for the hydrocarbon, and then draw the structural formula, and then based on the number of carbons, provide the name for the hydrocarbon. So the first one, we have CH3CH3. So of course it's a hydrocarbon. So it's going to contain carbons and hydrogens. And then I use superscripts to denote the number of carbons and the number of hydrogens. I have 2 carbons and 6 hydrogens. And so my structural formula, I'm going to connect the carbons together. And then I'm going to complete my structural, just a Lewis structure, by adding my hydrogen atoms. So now I've got my structural formula showing all of the bonds. And because this is 2 carbons, I remember my mother eats peanut butter. 2 carbons is E, so ethane. And so I'll also let you complete those last 2 in that table. And so another thing we want to note for our hydrocarbons that are alkanes that have all single bonds. And so their base formula is going to be CnH2n plus 2. For instance, ethane has 2 carbons. So it's N in this formula equals the number of carbons. So if ethane has 2 carbons, meaning that N is equal to 2, then it's going to have 2 times 2, which is 4, plus 2, which is 6. It's going to have 6 hydrogens. So if you know how many carbons a hydrocarbon has, you can figure out its chemical formula by using this base formula to figure out how many hydrogens that the alkane has. Now, if you're talking about an alkene that has 1 or more double bonds, its base formula is CnH2n. And then the alkynes, they have a triple bond. Their base formula is going to be CnHn. So it's going to have the same number of carbons and hydrogens if it's an alkyne. If it's an alkene, the base formula is CnH2n. So in question 3, these are both alkanes. They have the ANE ending. Of course, alkenes will have the ENE ending, and alkynes will have a YNE ending. So if we have 9 carbons, then the formula is going to be C9H2 times 9 plus 2, which is C9H20. And so I'll let you do part B for dodecane, which has 12 carbons. So take a few minutes and go into your group meeting rooms and finish up question 1. I've written the equations. You just need to balance them, and then complete table 2 and answer question 3, part B. So let's meet back in the general room at about 12:40. It's about 11:40. It's about 11:30 now. And I will pop into your group meeting rooms to check on you to see if you have any questions. I've posted the group numbers in the chat box if you need your group number. And so when we balance our equations, the numbers that we put in front of a reactant or a product is called a coefficient. So what coefficients are needed to balance part A, the glucose combustion? Do we need a coefficient in front of the glucose? Do we need a coefficient in front of the oxygen? What about CO2? What about water? What coefficients do we need to balance reaction A? Well, this one was already done for you earlier in the notes. So we need a 6 in front of the CO2 because we've got 6 carbons on the left. So we need 6 carbons on the right. We've got 12 hydrogens on the left. So we need to put a 6 in front of the water. Each water molecule has 2 hydrogens. So putting a 6 there gives us 12 total hydrogens. Now looking at the oxygens, there are 6 oxygens, 1 per water molecule there. And then the CO2, each CO2 has 2 oxygens. And if we've got a 6 in front of CO2, that gives us a total of 12 from CO2. So 12 plus 6 gives us a total of 18. So we need to put a 9 here to have, I'm sorry, we need to put a 6 here to have a total of 12 oxygens plus 6 oxygens with the glucose to give us a total of 18 oxygens on the left, as well as 18 oxygens on the right. For our methane reaction, we've got only 1 carbon on the left, and so 1 carbon on the right. We have 4 hydrogens on the left, so we need to put a 2 in front of the water to have 4 on the right. And then our oxygens, we've got a total of 4 on the right, 2, 1 per water molecule gives us 2. And then the 2 with the CO2 gives us a total of 4. So we put a 2 here in front of the oxygen. And then for the propane reaction, we've got 3 carbons on the left, so we put a 3 in front of the CO2. Remembering our rules from chapter 2 for balancing combustion reactions, you want carbons first, then the hydrogens, and then last, balance the oxygens. So 8 hydrogens on the left. So I need to put a 4 in front of the water to give me 8 hydrogens on the right. And then adding up the oxygens on the right, I've got 4 plus 6, giving me a total of 10. So I need a 5 in front of the oxygen on the left to give me a total of 10 oxygens on the left. For table 2, our chemical formulas, we've got 3 carbons for that second hydrocarbon, and we've got 4 carbons for that third one, and a total of 10 hydrogens. This CH2 in parentheses with the 2 on the outside, that 2 on the outside is for the carbon on the inside and for those 2 hydrogens on the inside. So therefore, you got a total of 4 hydrogens there and 2 carbons added to the other 2 carbons, giving us a total of 4 carbons and 10 hydrogens. And so we've got our structural formulas. And this, of course, will be propane with 3 carbons. And this will be butane with 4 carbons. And butane has a total of 10 hydrogens. In a lot of textbooks, you'll see it just represented this way with the lines. And it's understood that those lines are connected to hydrogens. And there's our structural formula for butane. So what is the formula for dodecane? It has 12 carbons. How many hydrogens does it have?
26.
Very good. Any questions about numbers 1 through 3 for section 6.2? And so energy is the capacity to do work. In classifying energy, there are two major types, potential energy and kinetic energy. Potential energy can be defined from the physics standpoint or from the chemistry standpoint. From the physics standpoint, the potential energy is energy that is stored energy due to the relative position of an object as far as its height from the ground. Whereas in chemistry, we define potential energy as chemical potential energy, and it's the stored energy that's in the bonds, in the chemical bonds of substances. Kinetic energy, however, is the energy of movement. So therefore, an object at rest has stored potential energy. When you move it and it moves a distance, that potential energy is converted into kinetic energy. So that's the physics definition and standpoint of the conversion of potential energy to kinetic energy. From a chemical standpoint, is if we have a substance, it's a chemical, it's got chemical bonds, you've got stored chemical potential energy in those chemical bonds. However, when you break those bonds, then you are therefore converting the stored chemical potential energy into kinetic energy due to those atoms being free to move and rearrange. Also, you have other intermolecular forces in, for example, in a liquid like hydrogen bonds, and therefore heating the liquid breaks those hydrogen bonds and therefore converts that liquid to a gas. That's also an example of converting potential energy into kinetic energy. And so therefore, something has to move a distance in order for work to be done on that substance or that object. So work is equal to the force applied to an object times the distance that it moves. So therefore, how much work is done on the object or the substance is equal to the kinetic energy of that substance based on the movement of that substance. And the kinetic energy is going to be affected by the mass of the substance and the velocity in which that substance moves. Velocity being the speed and the direction that that object moves. So therefore, the larger the object, for as the greater the mass, then that's going to influence the kinetic energy as well as how fast that object moves. Some other terms are heat and temperature. They mean totally different things. Heat is energy, and heat energy will always flow from a hot object to a colder object, whereas temperature is the measure of the average kinetic energy of atoms or molecules. And so temperature and kinetic energy are directly proportional. The greater the temperature, the greater the average kinetic energy of atoms and molecules. And so when we measure energy, we measure in specific units. One unit is the joule, the other is the calorie. The joule is the amount of energy that's required to raise 100 grams of a substance 1 meter against the force of gravity. The calorie is defined as the amount of heat required to raise the temperature of 1 gram of a substance like water by 1 degree Celsius. And so we can interconvert between the calorie and the joule. Now, when we say calorie, there are two types of calories. You have the lowercase c calorie, which is called the chemical calorie. And you have the uppercase c calorie called the dietary or nutrition calorie. So 1 chemical calorie is equivalent to 4.184 joules. And then we've got a few other conversion factors shown there as well. We can interconvert between lowercase c calorie and capital C calorie, for example. And then, of course, the kilocalorie, and then you also have the kilojoule. And we know the prefix kilo is equivalent to 1,000 of those base units. So if we have a slice of pizza and it contains 217 capital C calories, that's a dietary calorie. How much is this in lowercase c calories? And so we can first convert the capital C calorie to a kilocalorie. And then convert the kilocalorie into calories. And so all we're doing is converting units. The same principle that we learned early in the semester. You've just got some new conversion factors to play with. And because I know you're prepared for class, you've got your calculator. Now I want you to convert the same 217 capital C calories into kilojoules. So take a minute to do that. Do we have an answer? So anyone, your answer is 9079. .28 kilojoules. Does anyone disagree with that? I think you are a decimal place off. So we could take the capital C calorie and first convert it into the kilocalorie. They mean exactly the same thing, 1 to 1. And then convert the kilocalorie to a kilojoule. So it's only a two-step conversion. The next one, you got a bag of potato chips, has 70 kilocalories. And assuming that all the energy from eating these chips goes toward keeping your heart beating, each heartbeat requires 1 joule of energy. How long can these chips sustain a heartbeat of 80 beats per minute? So how long? So what are they asking you to calculate? What type of unit? How long? Time? So basically they're asking you how many minutes. Well, eating this 70 kilocalories from this bag of chips, how long will it sustain your heart beating? At a rate of 80 beats per minute. So to approach problems like these, start with what you know. Start with what you're given. I've got 70 kilocalories to work with. And I've got another little tidbit that's given to me. And you got to be able to extract out information from a question like this. That information is basically a conversion factor. You need 1 joule of energy per heartbeat. Does everyone agree that that is a conversion factor? So therefore, the chips are giving me 70 kilocalories. So I need to convert the kilocalories to joules because I'm given this conversion factor and it's in units of joules. So my kilocalorie is equivalent to 4.184 kilojoules. And I know for every 1 kilojoule, just by knowing my prefixes that I learned way back in chapter 2, I know for every 1 kilojoule, there is 1,000 joules. So my kilojoules cancel and my kilocalories cancel. So now I have joules, but that's not what they're asking me. They're asking me how many minutes. So now I can use this little tidbit and this little tidbit. So I need 1 joule of energy per heartbeat. It's just like solving a puzzle. Now my joules are gone. And my heart is beating at a rate of 80 heartbeats per minute. Now my heartbeats cancel. Now I've got the unit that I want. Minutes. Now I just need to do my math. Number 3, you've got a 12-ounce serving of soda. And that 12 ounces of soda has 92 kilocalories. In kilojoules, what is the energy released when metabolizing this beverage? So this is a simple one. I just need to convert my kilocalories to kilojoules. So when measuring energy changes, there's a specific type of laboratory device that's also used in industrial labs, especially food manufacturing companies use this to determine how much energy is in a particular type of food that they produce. And this device is called a calorimeter. And so you can use this device to determine the amount of heat energy that's released when a substance is combusted. And so what you can calculate is the heat of combustion. That is the amount of heat given off when a specified amount in grams or in moles of a substance burns in oxygen. And so heats of combustion are either reported in units of joules per gram or joules per mole. So if you test a reaction, like a combustion reaction, that releases heat, and heat is symbolized with the lowercase letter Q, what's going to happen when the energy or heat is released from that combustion reaction is what you have in your calorimeter is a device that holds your sample, and surrounding your sample container is water. So the heat that gives off, that heat is released from the substance that gets combusted, and that heat moves to the cooler substance, which is the water. So therefore, there's a transfer of the energy from the substance that's being combusted to the water that's surrounding the sample cup. And so that water temperature is going to increase, which can be read by using a thermometer. But most calorimeters now use a temperature probe versus a thermometer. And so in determining how much heat that gets released by burning the sample, the amount of heat that's lost by the sample being combusted is going to be equal to the amount of heat that's gained by the water. So the amount of heat gained is going to be equal to the mass of the water that's in the calorimeter times the specific heat of water times the change in temperature, delta T, of the water. The change in temperature is the final temperature of the water minus the starting or initial temperature of the water. And then you can calculate just by knowing the starting temperature of the water and then the final temperature of the water after the water's been heated. Then you can calculate how much heat is actually released by burning that particular sample. And so burning of fuel can be correlated to water flowing from the top of a waterfall. When the water is at the top of the waterfall, it has potential energy due to its relative height above the ground below. But then when that water starts to flow over, then that water has kinetic energy because now the water is moving. And so the energy that's released during the course of a reaction, you can think about it in that terms as well. You've got this stored potential energy in the chemical bonds. And then when the substance is combusted, those bonds break. And those bonds break due to that substance absorbing heat from whatever the ignition source is. And then once that substance combusts, the bonds get broken, and then heat gets released when new products are formed. So energy being a product of the reaction, energy getting released, that tells us that combustion reactions are exothermic because energy gets released during a combustion reaction. Each type of fuel that gets combusted releases a certain amount of energy. Methane gas, for example, releases 802.3 kilojoules of energy per every mole of methane that gets combusted. This is equivalent to 50.1 kilojoules per gram. And you just simply convert the moles to grams by dividing by the molar mass. And methane has a molar mass of 16 grams per mole. And so here we have our reactants, methane and oxygen. And we can see from the balance reaction, we've got 1. So whenever there's not a coefficient in front of a reactant or a product, then it's understood that you got 1 mole of them. So you got 1 mole of methane and 2 moles of oxygen. The combustion reaction takes place, and you produce CO2, 1 mole, and water, 2 moles. So you start off with a certain amount of potential energy that the reactants have. Heat gets released. You produce your products, and now you're here at this level, the energy of the products. And what the heat of combustion of methane, this 802.3 kilojoules per mole, is the energy difference between the reactants and the products. So that energy difference is the amount of heat that's released upon combusting the 1 mole of methane. So this energy difference is equal to the energy absorbed to break the bonds in the reactants, plus the energy released to form the bonds in the products. By adding those two energy values together, you get this energy difference of negative 802.3 kilojoules. That is equivalent to your heat of combustion for methane. So this week's lab is a lab in which you'll view this, the synthesis of biodiesel. And in testing the biodiesel that is synthesized, one of the tests that is going to be performed is a determination of the heat of combustion for the biodiesel. So different fuels have different chemical formulas. Here we saw the methane combustion reaction, but then you've got all the other hydrocarbons, the ethane, propane, butane, so on and so forth, and also other types of fuels like ethanol and water. I'm sorry, ethanol and wood and gasoline, which is mostly octane. So we can see here in this table, depending on the type of fuel that we have, we're going to have a certain energy difference. And that energy difference is our heat of combustion, which is symbolized with the delta symbol, which is the triangle symbol, and then a capital H, and then the COMB subscript. So you can see that methane has the largest heat of combustion, the largest amount of energy released. Notice the negative signs in front. Overall, combustion reactions are exothermic because you have a negative delta H of combustion, meaning that heat is released. So that negative energy difference, that means that heat is released. And that means overall combustion reactions are exothermic. So notice that wood, which is made up of glucose, has the smallest heat of combustion, only negative 14 kilojoules per gram. So you get more energy released when you burn methane, which that's the major component of natural gas, versus burning wood to heat a room. So we said that exothermic reactions is when energy is released. You get a net energy change that is negative. What that means is that the energy of the products are less than the energy of the reactants. And combustion reactions, of course, are exothermic. Endothermic reactions, on the other hand, are those that absorb energy. Their net energy change, which we call the energy difference, is going to be positive. And for endothermic reactions, the products have energy that is greater than the energy of the reactants. Photosynthesis is an example of an endothermic reaction that absorbs energy. So these two pictures demonstrate endothermic versus exothermic. For endothermic reactions, heat is absorbed. So heat is absorbed by the system from the surroundings. And your system is considered your chemical reaction. Whereas exothermic reactions, your system or your chemical reaction is going to release heat to the surroundings. So remember, endothermic reactions are those that absorb heat. Exothermic reactions are those that release heat. What would you consider burning charcoal in a grill, endothermic or exothermic?
Exothermic.
What about water evaporating from your skin? The process of evaporation, changing from a liquid to a gas. Do you absorb heat or do you release heat?
Exothermic.
So evaporation, that's like boiling. To boil water, do you need to release heat or absorb heat? Does water need to absorb heat or release heat to boil? Think about putting a pot of water on the stove to boil it.
Absorb.
Absorb, so that would be endothermic. So evaporation, same thing as vaporization or boiling. It's always going to be an endothermic process. You have to absorb heat in order to change from a liquid to a gas. The opposite is condensation, changing from a gas to a liquid. Condensation is exothermic, but boiling or evaporating is endothermic. What about photosynthesis? Glucose being made inside the leaves of a plant. What does the plant need to do to the sunlight? Release it or absorb it?
Absorb it.
So that would be endothermic. And what about ice melting? To go from a solid to a liquid. So think about taking a piece of ice out of the freezer, out of a cold environment, and you sit it on your countertop, a warmer environment. What is the ice doing? Is it absorbing heat to melt or is it releasing heat?
Absorbing heat.
Very good. That's endothermic. Think about the opposite. If you want to freeze some liquid water. So you take a glass, right? So freezing is exothermic. You have to release heat. Whereas the opposite, melting, is endothermic. You have to absorb heat. You got to get the ice to a higher temperature in order for it to convert to a liquid, right? So that means heat has to be absorbed to melt ice. Any questions about number 1? So 2 asks how much heat in kilojoules is released from combusting 1,250 grams of gasoline with an octane rating of 91. So to calculate the heat, we need to know the heat of combustion of octane times the mass of octane. Well, we know the mass of octane, 1,250 grams. But what about the heat of combustion of octane? Well, we can get it from this table. It's negative 44 kilojoules per gram. So therefore the heat, did I misspeak? Is the mass of octane 1525? No, the mass of the gasoline is 1,525. How much of that gasoline is octane? 91%, right? So 1525, change your percent to a decimal. And that'll give us how much of the gasoline is actually octane. So of the 1525, about 1388 grams of it is actually octane. So therefore our heat is going to be our delta H of combustion. That was 44.4 times the mass. And so we just do our math. And the amount of heat that's released is 6.16 times 10 to the fourth. And the units are kilojoules. So that's how much heat is released. And by me saying that the heat is released, I'm taking an account of the negative sign for our delta H of combustion. So you can always calculate the heat that is released by combusting a fuel if you know the heat of combustion for that fuel, which you can get from a data table like this. And then if you know the mass of that fuel. So when you're burning your gasoline, you've got other additives and things in the gasoline. It's the octane that's undergoing the combustion reaction. And that's what's releasing the energy to power your automobile. And so in closing our lecture for today, we talked about the fact that when we do a reaction and we convert reactants to products, the bonds and the reactants have to break. And this requires energy to be absorbed. Then the atoms are free to rearrange and form our new products. Forming bonds and making new products releases energy. So bond breaking is endothermic. Bond forming is exothermic. And then you combine the two processes together and you get your net change. If, when you get your net change, if it's a positive number overall, this is our energy difference, then you have an overall endothermic reaction. If your energy difference is negative, then your overall process is exothermic. And so bond energy is the amount of energy that must be absorbed to break a chemical bond, and also the amount of energy required to form a new bond is going to be that same bond energy, but with a negative sign in front. So this table here is very important. It gives you the bond energy for specific types of bonds. And so for the single bonds, you have a matrix set up here. For example, if I have a hydrogen-hydrogen single bond that exists in my H2 molecule, the bond energy is equal to, and in this table, the units for these bond energies are kilojoules per mole. So using this table, what would be the bond energy for an HH single bond? Well, I've got a hydrogen and a hydrogen, and so I use my table and see where those meet, 436. A carbon-hydrogen bond energy. I've got my hydrogen here, and there's my carbon, so that's 416. So that's how you use this table to determine the bond energies for single bonds. Now for the double and triple bonds, they're listed at the bottom of the table. So I want you to take a look at question 1 in section 6.5 before Wednesday. Using the bond energies in table 6.2, calculate the heat of combustion for propane. So we first must start off with a balanced equation. So we need to balance this first. I want you to do that. I think we've already did that in a previous question. So we've got to start off with a balanced equation. And then we need to rewrite the balanced equation, but this time using Lewis structures. See, now we're synthesizing. We're connecting concepts that we've learned in a previous chapter to solve a problem in our current chapter. And we've drawn the Lewis structures for CO2 and water so much that we should memorize how to do that in our sleep almost. So we've got the Lewis structures drawn for each product and each reactant, and it's balanced. I've got my coefficients. There's just the one propane, and we don't have to write the one if we don't want. We've got 5 oxygens, 3 carbon dioxides, and 4 waters. So why was it important for me to draw the Lewis structures for my balanced chemical reaction? Because we need to see the bonds, right? So we need to calculate how many bonds of each type are in each reactant, because those are the bonds that are going to need to be broken. And then we're going to have to multiply the number of each type of bond by the bond energy in this question to get the total amount of energy that needs to be absorbed to break all of the bonds in the reactants. Then we go to the product side, and again, we count up the number of each type of bond, multiply that number by the bond energy that's in the table, and then sum up all of those on the product side and put a negative sign in front, and that tells us the amount of energy that's released in order to form all the bonds that are in the products. And then we add up the total energy for bonds broken to the total amount of energy, which is going to have a negative sign, for the energy released due to bond formation for the products. Add those two together, and that gives us our overall energy or our energy difference. And if it's negative, then that means our overall process is exothermic. If that overall energy is positive, then that's going to mean our overall reaction is endothermic. So now that I've drawn the Lewis structures, use the bond energies in this table to calculate the heat of combustion for propane, and we'll start here on Wednesday and then do a few more examples using our bond energy table. So have a good rest of your Monday, and we will pick up here on Wednesday.